Okay. Any questions from last time which you do want them to be recorded, or any sort of discussions related to the material? So there's a rough recap of what we talked about last time. Any questions? Anything that was unclear you'd like me to go over again before we continue? Okay. And just a reminder, as is on the bottom of this slide, first homework is out. It's due on January 29th. This Friday at 11:59 p.m. Hopefully it won't ruin your Friday night, so try to maybe take a look at it before. Last time we talked about mutual information, which is some way of measuring dependence between two random variables, or and you can again define variants of it when it's conditioned, or you can write a chain rule for it when one of these random variables itself is a tuple. This is not quite the same as mutual information for more than two variables, because it's just like X is a big random variable. And in the homework, there is a question about trying to define mutual information for three variables. It's actually not very clear how to do it. There are some candidates, but each of these has their own problems. Like we saw an example last time where there were three random variables, but every two of them were independent. So you can't really define pairwise mutual informations. And some other candidates run into other issues. And in fact, this is one of the main bottlenecks in proving communication complexity lower bounds in multi-party model, for those who know that application. But it's actually just, there is no good definition of mutual information. Okay, but yeah, take a look at the homework. We also talked about data processing inequality, which is if you have X, Y, and Z, which where Z depends on X only through Y, or and in special cases, Z could be a function of Y, then the mutual information of X and Y is at least as large as the mutual information of X and Z. Okay, this is all from last time. If you have any questions about it, you can ask me now, or also just stop me later and ask them, so no worries, but let me continue. Okay, and we kind of stopped here last time, which is an inequality which just uses this notion of this kind of Markov chain, and it'll be fairly useful later when we are trying to do sort of hypothesis testing, or like you have data which could come from distributions with different parameters, and you're trying to understand the parameters of these distributions, you're trying to learn the parameters. And a simpler problem is at least you have some 20 choices for the parameter, figure out which is the right one. So, and this is how roughly a lot of bounds are proved. And Fano's inequality is kind of an important tool for that, especially when you have more than two choices. For two choices, there are other methods which we'll see later today and tomorrow and next lecture, which can give stronger bounds. But for many choices of parameters to learn from, Fano's inequality is an important tool. Okay.
Sorry, Madhur, what do you mean choices of parameters? You're saying it's like there's like P and Q, and you're choosing between P and Q for like coin biases, or?
Yeah, so I mean, think of so this is in the learning setting where let's say you have a Gaussian, and it could be one of 20 possible Gaussians, and you're trying to figure out which. And if it's one of two possible Gaussians, there is maybe even stronger things you can say. But when it's one of 20 possible, Fano's inequality is often the tool of choice. I think this is not strict. There are many other kind of techniques, but these are some representative ones. Okay. But for now, let's just think of this Markov chain, which is you have some hidden data, parameter, whatever you want to think of it, some hidden ground truth, X. You don't know what it is. And this generates, or sort of, there is another random variable Y, which you can think of as kind of coming from X, or which is maybe some data. And then based on this data, usually you will sort of have some sort of prediction for what X is. And this usually would be just a function of the data. So you would have a predictor for X, which we will call X hat. And you want to understand what is the likelihood that you will correctly predict X based on your observation of Y and use of this predictor. And in particular, we denote the probability of making an error, which is by P sub E, which is the probability that your prediction value X hat is not equal to X. Note that we are always talking of sort of finitely supported random variables so far. So everything is finite. This sort of makes sense. If it's infinite, then so essentially always not equal. So, but let's say we are talking of finitely many values. And the universe of possible values is script X as always. And then Fano's inequality says it's some lower bound, but you can think of it as a lower bound on this quantity P sub E, which is the probability of making an error. And it's some lower bound in terms of the entropy of P sub E and in terms of the number P sub E itself. But a lot of the times the way it's sort of used is by saying that the entropy, the binary entropy of P sub E is at most 1. So at the very least, this implies that P sub E is greater than equal to h of x given y minus 1 divided by log of.
Madhu, maybe I have a naive question. What does it mean when you say two random variables, like the two random variables are not equivalent? I just don't understand.
Not equivalent as in their values are not equal, just
how I define this. Yeah.
Is it that their values are not equivalent for some like omega in their sample space?
Right. So, I mean, remember what a random variable is just a function, right? It's a function of omega. So you can think of it as that something happened in your probability space, you sampled an omega, and then computed the value of the function X and the value of the function X hat. And these two values came out to be unequal. Right? Or you can think of it just as a simple example, you can think of X and X hat are just coins. And the value being unequal just means that one of them came out heads, the other came out tails. But that, yeah, it's not anything about the functions being non-equivalent. It's just the values of the function being not equal. The probability is over omega or over the underlying space. So once you pick an element of the underlying probability space, then it's just the value of X hat is just some element of this finite set script X. Does that make sense?
Yes, thanks.
Okay. Right. So this is a consequence that I wrote down. It's a but yeah, I mean, I kind of wrote the more general inequality here.
And another trivial question.
Please, yeah.
The cardinality of X is the number of outcomes and like the support of X. That's the size of support of X.
Yeah.
Okay.
So this is the support of X or the support of X hat. I'm thinking of both of them being the same. Okay. All right. One sort of change of notation. I'm sorry for it, but I kind of denoted the binary entropy by H sub B. I'm going to use H sub 2 here and later, just because it also generalizes nicely when you have the query entropy, which actually does come up in coding theory. H sub B and H sub 2 are both used in literature, so you might encounter both depending on where you are reading. But yeah, sorry about that. I used H sub B, I think, previously, but I'll switch to H sub 2 today and later in the course. Okay? And also amend the notes. Okay. So the proof of the inequality is actually not too complicated. But it sort of illustrates an important sort of trick which comes up all the time, which is to introduce an extra random variable which is 0 or 1. So, I mean, it's sort of partly is evident from the statement here that we are looking at the binary entropy of the number P sub E. And so binary entropy of the number p sub e is just the entropy of a random variable, which is 1 with probability p sub e and 0 with probability 1 minus p sub e. So it's just the technique is to introduce a random variable, let's call it e, which is, as the name suggests, is going to denote when an error occurs or when x is not equal to x hat. And this is going to be 1 if x is not equal to x hat, and 0 if x is equal to x hat. Okay. And so makes sense from the definition that the probability that e is equal to 1 is exactly p sub e, and the entropy of this random variable is equal to the binary entropy of the number p sub e. Okay, so, and then we'll encounter this quite a few times, this sort of indicator random variables, which are 1 or 0. We already saw one when we were doing Shearer's lemma, but we only cared about its expectation. And now we'll also talk about entropy of these things. Once you have this in place, then the analysis is, like the proof is relatively simple. So let's measure the entropy of what we don't know, given what we predicted. Okay. And I mean, given x hat, okay, one other reason for that is we want a bound in terms of entropy given x hat. So it's not an unreasonable entropy to consider. And I mean, and okay, and let's all right, so we have entropy of two things. We can apply chain rule and write it down. So let's do that. Okay. So by chain rule, we can write it as entropy of x given x hat, which is great. That's a term we want. And entropy of e given x and x hat. Now I claim that the second term here is very easy to understand. I see some people nodding. Would someone like to say why?
Once you know x and x hat, e is just whether they're equal or not.
Right. So e is completely determined once you know x and x hat. So the entropy of e is actually 0. E is just, once you know the value of x, you know the value of x hat. And remember, this entropy is just over sort of expectation over possible values of x and x hat. Once you know both those values, the entropy of e given those values is 0. So this is 0. So what we wrote is actually just a rewording of the right-hand side. Okay. So that's just one way of considering the entropy of x and e given x hat. Okay, that was fun. Let's do that again. So let's write this entropy again, but now expanded the other way using chain rule. Okay, now the first term is sort of one of the terms we want on the left-hand side of our inequality. So let's get it. So because conditioning on average reduces entropy, let's just write it as h of e. And now the second term is something which involves e in the conditioning, and when we condition on something, it means we kind of take an average over its possible values. So let's take those possible values. So this is equal to the probability that E is equal to 1 times the entropy of X given E is equal to 1. And I'll leave the conditioning over X hat intact, plus the probability that E is equal to 0 times the entropy of Now, again, I claim that the last term is very easy to analyze. And for exactly the same reason. If we know E is equal to 0, we know that X is equal to X hat, and we are given X hat. So we know X. So this is also 0. The first term here, or the second term in this expression, as we already know, is P sub E. Okay. So there's only one term left. It kind of better behave as we want it to. So it should be upper bounded by log of size of X minus 1. I mean, first, it's certainly easy to write a log of the size of X because, or this space script X, because the random variable X is supported inside this space script X. So log of the size of the space is an upper bound on the entropy. And actually, given X hat, it's and given that E is equal to 1, it's supported on a space of size 1 less. Because if we are given X hat, we know for sure that it can't be whatever X hat is. Right? So, so that is why this is less than equal to log of. Again, doesn't sort of make a big difference when the size of X is pretty large or when the space is pretty large. But when you're applying it to a space of size 2, it will sort of make a difference. Okay, that's Fano's inequality. Okay, we proved the first greater than equal to. What about the second greater than equal to?
Data processing inequality.
Yeah, data processing. So, so if you add h of, or if you kind of subtract both of these from h of X, you will get mutual informations, and we just kind of rearrange the data processing inequality to give you this. Okay, good. So that's Fano's inequality. Now let me get to an example which is sort of slightly combinatorial. It's used in some lower bounds in circuit complexity. But it kind of, I mean, I'll do a very kind of simple case of it. It illustrates sort of the point that I was making last time, that mutual information can become more interesting when you're trying to design or choose these random variables X and Y. In this case, I mean, X is kind of given, Y is what you are choosing, subject to certain conditions, or where you have the freedom of choosing one of these variables. Okay. And then, yeah, the behavior of the quantities can be very useful. Okay, so formally speaking, graph entropy defined by corner graph and hypergraph entropies, it is defined as the minimum mutual information between two random variables X and Y. So X and Y can be arbitrarily correlated. What the conditions we are given is just in terms of what they look like. I mean, okay, there's some condition on the correlation, but X by itself is completely specified. If we just look at sort of the random variable X, it's a random variable which is uniformly distributed over all vertices in the graph. Okay. More generally, you can have some specified distribution of this random variable, and the sort of that distribution can be P, and then you will define the graph entropy with respect to the graph and some distribution. But let's look at this simpler case. Okay, so X is uniform over all the vertices. Y is something which we get to choose. It can be arbitrarily correlated with X, but there are a couple of conditions. One, Y is going to be a subset of vertices. It's not a single vertex. It's going to be a subset, so denoted here in yellow. It's going to be an independent set, which means it's going to be a subset of vertices not containing any edges. So the graph is given for any given subset, we can decide whether it has edges or not. And it should contain X. Okay, so that already tells you that it can't be quite independent of X. It has to, right? So the mutual information can't be 0. The question is, how low can we make it? I'm defining it as a mutual information, calling it as an entropy because it was sort of defined as an entropy rate when the graph kind of corresponds to some symbols you want to transmit, but the edges are things where it's okay if, edges are places where you don't want to use the same code word for two things which are joined by edges. Elsewhere, you can use the same code word and so on. And if you repeat this process m times, what is the best entropy rate, or what is the smallest message you can send? So it was defined in terms of that. It defined as a limit, but the limit comes out to be equal to this number. So let's just talk of the mutual information here. And so, yeah, is the definition, at least in terms of mutual information, okay? Okay, good. So I'll put the definition here again, and I'll ask you to compute it for a couple of things. So let's start with the complete graph. And actually, I realize now that the graph I drew is not complete. So let me complete it. Okay. So a complete graph is one where all pairs are edges, or sort of all edges are present. And now we want to sort of minimize this mutual information with the conditions on X and Y. So X is going to be a random vertex, and then we can define Y. I claim that there's not too much freedom in designing Y. Can you tell me why?
I mean, you can only choose one vertex at max, right? Because if you choose any two, there will be edge.
Yeah, and what is that one vertex?
Y is independent. So, I mean, that's the same vertex as X. So,
yeah, Y has to contain X, and it can only contain one vertex. The moment you pick 2, there is an edge. So Y has to be equal to X. Okay, so there is nothing much you can do. Y has to be equal to the set X. But that means that the mutual information which is h of X minus h of X given Y, the second term has to be 0. And because X is uniform, let's say the number of vertices of the graph is n. Yeah, I denoted it by k sub n. So it's log n. So the entropy of the complete graph is easy. Now, the entropy of a bipartite graph, I claim sort of goes on the other extreme. It's actually very small. Any guesses or any suggestions what to do? So remember, we have this freedom in choosing Y. X is going to be a uniform vertex. So, and the bipartite graph, again, as drawn, I didn't necessarily draw a complete bipartite graph, but you have two, like you partition the vertices into two subsets, and the edges only go across. They never are within the same side. And yeah, we have a lot of freedom now in designing Y. Can you suggest some good choice for Y?
The partition in which X is.
I'm sorry?
Just choose the entire partition in which X is.
Right. So, I mean, it's kind of drawn suggestively. So if X is in the blue set, we take Y to be the blue set. If X is in, I'm not necessarily saying that this is an optimal distribution, but this will give us an upper bound. So let's see what upper bound we get out of it. The good thing with this is that if I give you Y, you don't learn much about X. So let's see. Or another way to put it is that, so there are only two subsets. So let's see. So this is equal to the mutual information of X and Y for whatever Y we designed, or it's actually less than equal to the X and Y that we specifically chose. The mutual information is, I mean, you can calculate it in both ways. I'll work with this definition, let's say. Both of them can be used to give the same answer. H of Y minus H of Y given X. It's at most H of Y, the second term is non-negative. And H of Y itself is actually pretty small. So Y is the blue set with some probability, and okay. So Y is a binary random variable. So and green with some probability. And let's say the number of vertices on the two sides is N1 and N2. Or let's say L and, let's say N1. Sorry, let's just say B and G. Okay, so it's blue with probability B divided by B plus G, and it's okay, let me just use N because I'm going to use it for parameters. It's blue with probability N1 divided by N1 plus N2. And it's green with probability N2 divided by N1 plus N2. Because X is a random vertex and Y is going to be a set containing that random vertex. So a random vertex lands on the left side with probability N1 divided by N1 plus N2, on the right side. So in particular, it's the binary entropy of the parameter N1 divided by N1 plus N2, which is less than equal to 1. It's the binary entropy of something. There are two choices for Y. So actually, I didn't even need to calculate the probabilities if I just wanted. And this, I claim, is already enough to prove some sort of special case of some formula lower bounds that was studied. But as an exercise, I'll let you check that if you know the size of the largest independent set in your graph, then you can get a lower bound on the graph entropy. So, and the bipartite graph case can show you that it's at least somewhat tight. Okay, I'll leave that as an exercise. We need one more property, which is before we kind of apply it, is that it's subadditive. So if you have a graph G, which is a union, or which is, let's say, even contained in the union of G1 and G2, by which I mean that the vertex set is the same. The edge sets of the union of the edge set of G1 and G2 gives the edge set of G. And you can replace equal to the union as by being contained in the union, because you can always add a third graph and that will have non-negative entropy. So, and then I claim that the entropy of G is less than equal to the entropy of G1 plus the entropy of G2. All right, let's try to prove this. Now, this is a little more interesting because we can design whatever X and Y we want for G. We are given some X and Y, which are maybe the optimal ones. So we are maybe given X and Y1, and we are given X and Y2. In fact, technically we are given variables X1 and Y1, and we are given X2 and Y2. But X1 and X2, I mean, they correlate with Y's in some weird ways, but they look identically distributed. So X1 and X2 are both uniform. on the vertex set. So, and now the goal is to design X and Y, which give us a low mutual information or low graph entropy for G. And by the way, Y1 and Y2 are independent sets in G1 and G2, and now whatever Y we design should be an independent set here. Any suggestions? Let's write down everything we have to work with, right? So X we need to design, which is uniform. And then Y1 is independent set in G1, Y2 is independent set. And we need Y to be an independent set in G, which is G1 union G2. Okay. Okay, there is a suggestion, partition support of Y into, so G1 and G2 have the same vertex set. So the support of Y is subsets of vertices, and G1 and G2 both have the same vertex set. So we can't quite partition the support of Y into G1 and G2. They have different edges, but the vertices are the same. So now, okay, let me put it another way. You are given an independent set in G1. You're given another independent set in G2. Can you come up with an independent set in G? Great. Okay. Yeah, so I got 2 votes for intersection. So, so we can take Y to be Y1 intersection Y2. And so Y1 contains X1, Y2 contains X2, and we want Y to contain X. How should we choose X? And the distributions are the same, but somehow this is a probability space where we are defining joint distributions. So we want to make sure that X now lies inside the intersection of Y1 and Y2. Okay, I mean, I'm making it maybe seem more complicated than it is, but the point is, we can always make sure that we choose X so that it's that the X1 and X2 are both equal to X. So in other ways, you have a joint distribution for X1, Y1. You have a joint distribution for, so you have a distribution for X1, Y1, and you have some joint distribution for X2 and Y2. And both of these are the same, have the same marginal over X. So X looks the same, uniform. So now we can define as follows. So pick X uniformly, and then sample Y1 conditioned on X, so Y2 conditioned on X equals little x. And okay, so we can just make sure kind of by fiat that these two distributions will agree on the X part. Okay, we'll just sample the X first, and then we have joint distributions which will tell us how to sample Y1, how to sample Y2, and then we'll take their intersections. This is a common construction. It has a sort of added advantage that given X, Y1 and Y2 are independent. So this is a common way of combining two joint distributions. Okay. And once we do that, the proof is actually very simple. So now we're trying to look at the mutual information of X and Y, which is the mutual information of Y1 intersection Y2. Right? That's how we defined Y. I claim that this is less than equal to the mutual information of X and the tuple Y1, Y2. Any guesses for why this is true? You have to be a little more careful kind of adding, subtracting stuff and conditioning in mutual information, as we saw with respect to entry. But here I say that this is true and easy from what we have done so far.
One of the data processing steps?
It is data processing. So Y1 intersection Y2 is just a function of Y1 and Y2. If you know Y1 and Y2, you can compute Y1 intersection Y2 yourself. So it's still data processing. So it's let's see. And Y1 and Y2 are just chosen so that they are independent given X. So the second term we can split conveniently. And now to get mutual informations, all we need to do is split the first term, but that's easy. That's subadditivity. So just rearrange. That's just subadditive. And this step uses the conditional. Okay. Once we do this, we're kind of done. We have the upper bound we want. And it gives a fairly useful proof of the following. I mean, you can ask it as a combinatorial question, which is just that suppose you have the complete graph and you want to write it as a union of a bunch of bipartite graphs. How many bipartite graphs do you need? And this is a special case of kind of formula lower bounds, which were being studied by Newman and Wigderson, where you are trying to look at formulas which are of the form, you have an OR gate, followed sort of with a bunch of AND gates. Each AND gate has like 2 OR gates again. And each of them can, so it's like a depth 3 formula. It's and each of them can take multiple variables. So, I mean, more generally, this kind of formulas are called De Morgan formulas, and they gave a lower bound on the size of De Morgan formulas in general for a relatively simple function, which is a function on 0, 1 to the n to 0, 1, which is just something which checks that x1 plus xn is greater than or equal to 2. So at least 2 of the bits are 1. You can think about why checking this by a formula of the above type corresponds to covering the complete graph. intuitively, yeah, I mean, okay, you can think about it. Just sort of the edges of the complete graph denote like the two variables which if together are true, then you will get 1 in the formula. And why the covering with bipartite graph corresponds to the circuit structure, you can check. But they actually proved a bound which works for more general De Morgan formulas using the same sort of concept of graph entropy. And here the bound is very easy because based on what we just saw, we can write down that the graph entropy of the complete graph is less than equal to the graph entropy of G1 plus the graph entropy of GR. Now, by definition, these are all bipartite graphs. So the entropy of each of them is at most 1. And the entropy of the complete graph, as we saw, is equal to log n. So you need at least log n bipartite graphs to cover it. I might be missing some constants or being a little loose with those, but you can check that this is typed. At least when n is a power of 2, let's say. Otherwise, you can just kind of move n a little so that it becomes a power of 2 and won't change much in the bounds. Okay. So yeah, I mean, I won't go too much into this application, but it's a nice paper and it sort of simplifies a bunch of other bounds. If you're interested in this kind of stuff, you can take a look. There are also some more recent presentations of these. But yeah, it's a nice application of this sort of graph entropy or the generalization to hypergraphs. Okay, any questions?
Wait, here is this bipart. So where does the bipartisaness come from? Is it like the successive layers are bipartite graph? Or?
The bipartiteness actually comes from the fact that the AND has 2 inputs. So, okay, I mean, just to kind of give away the game, you can think of the, I mean, yeah, I'll ask you to fill in some more details, but let's say this OR is over a set S1 of variables, and this OR is over a set T1 of variables. And so intuitively, you can think of it as adding all edges between the set S1 and the set T1. If any 2 of those variables are true, then this kind of sub-formula will be true. Because OR of everything in S1 and OR of everything in S2, and then you're putting an AND. So it will cover all the edges of the bipartite graph, which comes from some pair with 1 vertex in S1 and 1 in T1. And similarly, you can think about the rest of the formula. Each of them will be a bipartite graph between S1 and T1, and they will cover the edges. You can think about why intersections between S1 and T1, what they do, etc., etc. Okay, I'll leave it up to you. But feel free to ask me more after the class or in office hours if you like. Does that
question is like, so in this notion of graph entropy, why, like, what is the importance of independent set, like, apart from this application? Like, there, it seems like that notion could be a kind of arbitrary, right?
Yeah. So, I mean, I didn't actually cover the definition which the notion of independent set. I mean, here it's useful, but it didn't really, the definition didn't come for this application. It came from the fact that we wanted to kind of send a code word corresponding to, or like one code word for every vertex of this graph, such that across any edge, the 2 code words are not the same. This is a coloring of the graph. Just each code word can be thought of as a color, and all we want is across any edge, they are different. And a coloring is always a partitioning of the graph into independent sets, because of course a single color class cannot contain, cannot contain an edge. That's by definition. Just we said that 2 points across an edge have to have different colors. So each color class is an independent set, and so you kind of think of that definition with like take limits over not sending one symbol, but kind of looking at 2 copies of the graph or m copies of the graph, and so on. And once you work with that definition, the mutual information with respect to y, which is an independent set, sort of comes out of that. But intuitively, it makes sense because of this sort of coloring definition, or just wanting to make sure that things across an edge are different. Does that make sense roughly? But
Yeah.
okay. All right. So let's move on to the next concept that we will talk about, which is KL divergence or Kullback-Leibler divergence. Again, this is one way of measuring how different two distributions are. So far we were talking of random variables, and as I said in the beginning, we have a random variable x and we have a distribution p of x. We were just kind of hiding the distributions because we had just one underlying probability space, and we were talking of random variable x, y, and whether they are correlated or not, x, y1, y2, whatever. This is a little different. So this is talking about two distributions for the same random variable. So random variable as a function on the probability space is the same. The underlying measure on or the distribution on the space is changing. And so we have p of x and q of x, which are the distribution for the same random variable, same support, same possible set of values, but different probabilities. And we are trying to understand how different these two distributions are. Even in this kind of specific task, there are many ways of distinguishing two distributions. We'll see at least one more during this lecture itself, and you'll see more in the homeworks. So this is by no means a unique way of kind of trying to distinguish two distributions. It turns out to be very convenient, and we'll say a little bit why. So, but the way it's defined is you're given two distributions P and Q on the same support, or for a random variable with the same support. And now, because the random variable is the same, we'll use the same sort of cheat, and we'll kind of hide X and just talk of P and Q. Later, we'll get to situations where we won't be able to cheat at all. We'll have to write the random variable and the distribution, everything. But for now, I'll try to cheat. So, right, the KL divergence just denoted D of P and Q, or D between P and Q, which is just sort of like an entropy-like definition that you have P of X times log of something. But instead of the log being 1 over P of X, it's a P of X divided by Q of X. You can view it by just sort of splitting this sum into two parts. And it's one interpretation, which is comes from the Shannon code, where we thought of the entropy as telling us what is the right way to encode a random variable or send messages if we know the distribution for the random variable. That for a symbol little x, we should design a code word with length log 1 of P of X. So, and here we can kind of view it as, suppose the true distribution for the symbols was P, but I didn't tell you that. I told you that the distribution is Q. So you went to the first lecture, you designed the best code where the code word length for the symbol little x was log 1 over Q of X. But then I gave you the wrong information. Okay, let me not overuse the word information, but I told you the wrong distribution. So how much did we lose because I kind of told you the wrong distribution? What is the loss in code word length in expectation? So the first term is the expected length of a code word according to the scheme you designed, where the sim is sort of the value little x had a code word of length log 1 over Q of X. The second term is the entropy, which, as we saw, is the best code word length we can hope for. And what we lost is the KL divergence. So it's some way of measuring, and it turns out to be convenient for some statistical applications that this is really the right form that shows up in certain bounds. But at least it makes sense that it's some way of saying like how much P and Q differ. Sometimes just the first term is referred to as cross entropy. Yeah, because you crossed up P and Q and defined the entropy somehow weirdly. I don't know. But is the definition and this interpretation, does it at least make sense? Any questions? Is everyone happy with this definition? Okay. If you're happy, then I'll ask you to calculate. So let me give you two distributions, relatively simple ones. The support size is 3. And Q is just uniform. P is kind of uniform in the first two things. What is the divergence of P and Q? And also I've written down the divergence of Q and P. Note that as written, at least the expression is not symmetric. So these will be different expressions. You have to tell me what the answers are. Right.
Log 3/2 and ill-defined.
Okay, log 3/2 and ill-defined. All right, let's see. So this one is half times log 1/2 divided by 1/3 plus half times log 1/2 divided by 1/3 plus 0 times log 0 divided by 1/3. And kind of said that 0 log 0, if we take limits, is we define it to be 0. And so the third term in this computation is 0, and the first two terms come out to be equal. So we will get log 3/2. All right. Let's look at the second one. So we get 1/3 log 1/3 over half. Okay. So the last term technically is infinity because it's a log of 1/0. 1/0 is infinite and log is an increasing function. So if you, instead of 0, try to take a limit, it will be infinity. So this, I'll call it infinity. Okay. Or so it illustrates a couple of useful points. One, this KL-divergence as defined is not is not symmetric. P and Q, like the KL-divergence of P and Q and P can be different. Sometimes it's called P with respect to Q or the other way around. So it depends on the order in which we write things. It's not even bounded. So as we saw this example, it's going to infinity. And of course, I can make it as large as I want just by changing the 0 to epsilon. Okay. But at least it has a saving grace that it's non-negative. So it's some measure of distance. And that we kind of sort of intuitively already saw because we said this is how much extra do we pay for encoding according to Q of X when we should have encoded with respect to P of X. So, but because the encoding with respect to P of X is the best possible, we should pay at least something. That's one way of thinking about it. We can also just prove it more formally from the definition. Now, we should be a little careful. As we saw last in this example on the previous slide, if the denominator is 0 somewhere, then we can have infinities appearing. So we need to be a little careful about saying that we should have the fact that if Q of X is equal to 0, then P of X should be equal to 0. So that we only get 0 times log of 0/0, which we can take to be 0 because of limits. I mean, but this is easy because we are trying to prove things are greater than equal to 0. If not, then we get infinity. Because the term in front, which is P of X, is non-negative. So we will get infinity, which is always greater than equal to 0. So we don't need to worry about it. And so we can assume, sort of without loss of generality, that Q of X is greater than 0 always. Because if it's 0 somewhere, then P of x will also be 0. If P of x and Q of x are both 0, we can just not consider this element in our support anyway. We can just throw it out of the space script x. So we can just assume that Q of x is greater than 0. I mean, yeah, we will need to be careful with KL divergence. I'll not always say this, but at least let me just mention that you need to be a little careful. Okay. Once we do this, it's easy. Maybe there are a couple of ways of doing this. Let's, as before, when we were trying to kind of upper lower bound entropies, we used Jensen's inequality. We'll try to do the same. Log is a concave function, which is good for upper bounding. So if you want to lower bound, either we should look at negative log or we should look at some other function which is convex. And you can do it this in two ways. You can either look at negative log or x log x, which are both convex functions. So let's try one of them. So I can, let's say, multiply and divide by q of x. Okay, and now it looks of a nice form. I can think of it as expectation of y log y, where y is equal to p of x divided by q of x with probability q of x. This is just the same as in the upper bound on entropy. Now we're just kind of looking at the function y log y rather than log y because we want a lower bound. Because of Jensen's inequality, we will get that this is greater than equal to expectation of y times log of expectation of y. And let's just calculate the expectation of y. It's 1. So we get 1 times log of 1, which is 0. So the KL divergence is always non-negative. Again, you can check that it's equal to 0 if and only if we get P is equal to Q. This is, we've seen this before in sort of conditioning reduces entropy, when does equality hold and so on, or when does equality hold in case of just the upper bound and entropy. It's the same. You sort of look at strict convexity and then just try to say Jensen's time. Okay. So that's KL divergence. Any questions before we go further? Okay. So as for other quantities we have studied, there's a similar looking chain rule. And in some sense, chain rules are the whole reason information theory is quite useful in various applications in statistics and computer science, because it gives us convenient ways of analyzing sort of many samples or many events in terms of these atomic or small events, which are much easier to write down. And we'll see applications of this in a few minutes. But now it's a slightly different or slightly more involved situation where we have random variables x and y. We have joint distributions on x and y, and two different joint distributions. Both of them may be conditioned on x or not. So I'm writing things more explicitly. We're writing the distribution of x and y. When I say p of x, it's then you take the joint distribution p of x, y and just marginalize or just look at the distribution of x according to it. Same for the conditional distributions. And q of y conditioned on x, where x is a random variable, is again defined as before as an expectation over values of x. And then we'll see that in the proof. So, but is the notation, maybe except for the very last term, does the notation make sense? we have two distributions now on two random variables, x and y, and these are both joint distributions. We're denoting them by p and q. Okay, the proof is actually just calculation. So, but it's good to see it. So, so let's write down the left-hand side. It's let's write down the probability, and my notation is that I'm always using lowercase letters for actual probabilities. Although, yeah, if you think of capital P as a function, doesn't make a difference. But just sort of adding a little redundancy. Okay. And P of x comma y is the joint probability of the value little x and the value little y. There's sort of only one way to split it in terms of the value for x and the probability for y given x, which is Bayes' rule. So, or I mean, rather than just the definition, I guess. But, and now that we sort of have a log of the product of two things and we want a sum of two things, again, there's only one thing to do. So, all right. Up to this point, we've just been following definitions. Now, the only interesting thing is just kind of how we rearrange these summations a little bit. So for the first one, we can take the summation over y inside. So we can write it as summation over x and summation over y, because the log part doesn't depend on it. And this is what we actually defined to be P of x. I just said P of x is the distribution you get by just sort of marginalizing over x, or rather summing over all y's that can occur with a given x. The second term is again, we just sort of split it so that we get something outside which looks like what is inside the log. So we can write it as P of x times P of y given x. And now things start to look the way we want them. So we have summation over x, P of x log P of x divided by Q of x, plus summation over x, P of x times summation over y, P of y given x log okay, sorry, so slightly boring proof, but this is nothing but the KL divergence of P of x and Q of x. And this is the expectation over x sampled from P, which is kind of hidden when we wrote it this way, of the KL divergence of P of y given x equals little x with respect to Q of y given, which is just what we are calling this as a shorthand as before, but here we are kind of cheating even more than usual, because x could have been sampled from P or Q, and it's important that it's sampled from the first one, and we didn't, the notation there doesn't quite make that clear, but again, this is how commonly it's written. Any questions about this? Okay. As before, if X and Y are independent in both these distributions, then you can do something better and so on. We'll see some examples, but for now, let's just remember this chain rule and we'll come back to it. And for one application, we'll kind of see a relationship between one other way of measuring how far two distributions are. And this is something called the total variation distance or the L1 distance between two distributions. Okay. I mean, you can think of it as, if you think of the distributions as just sort of vectors with the numbers P of x1, P of x2 as a list, then this is just the L1 distance of the two vectors, which is just look at the difference of the two vectors and look at the coordinate-wise sum of absolute values. You can scale by half and it will become clear in a minute why that is a little more natural. But it's called the total variation distance between two distributions. It's has a nice and natural interpretation. It's the best distinguishing probability between these two distributions if I only give you one sample. So you have an algorithm which knows a lot about how the distribution P is, how the distribution Q is structured. It knows a lot about how the supports of the two look, where P puts more probabilities, where Q puts more probabilities. And your algorithm is now trying to tell me whether a sample I gave you is coming from P or was sampled according to Q. So let's say this algorithm can be thought of as a function which answers 0 or 1. Okay, let's say 0 for P, Q for 1 for Q, or the other way around. And now I'm just going to check, if I gave you a random sample from P, how often did you say P? Or if I gave you a random sample from Q, how often did you say P, or how often did you say Q, whichever I want. But so in particular, if I check how often did you say 1 in both cases, the difference of these would be how much you distinguished between the two distributions. And I claim no matter what algorithm you have, no matter what statistical test, no matter how much it knows about P and Q, the best it can do is the probability of distinction is the total variation distance between P and Q. So it's the efficiency of the best one sample classifier, if you want. So, I mean, it doesn't seem very interesting to do one sample classification, but P and Q could be distributions on n tuples. So, and then we'll see this as the next example. So I have a coin, I tossed it n times, and now I called this big n tuple as one sample of the product distribution. Okay. And I gave you this, and I said, okay, what can you tell me how I sampled these n coins? So now this is one sample from a product distribution. So this one sample language is fairly generic enough. It's just n samples are one sample from a product distribution. So it's not restrictive. It's just the statistical distance, or it's called the statistical distance or total variation distance, whatever, of P and Q. Okay. Any questions about the definition or the statement of the result? We'll prove it in a minute. Okay, so let's prove it. It's again, more or less follow your nose kind of proof. So let's just write out whatever we have. Okay. So let me couple the two terms and write. So it will be P of x times f of x and Q of x times f of x. Let me just write it once. And I'm looking at the absolute value of the two of this. Now, it's sort of, to get this half, I'll basically, instead of thinking of f as a 0, 1 function, I'll think of it as a plus minus 1 function. So the trick for that is just that I subtract and add half to f. So I just added and subtracted half. But the second term is kind of easy as before. Summation over x p of x is 1. Summation over x q of x is 1. So it's just half minus half, it's 0. So that term is just doesn't really matter. And the first term now we can analyze relatively easily. It's equal, sort of is less than equal to summation over x, p of x minus q of x times f of x minus half. Okay, and this quantity is always less than equal to half in absolute value. It's either 0 minus half or 1 minus half. And the sum of all these terms is just the L1 norm of P and Q minus Q. Okay. Nothing special about a 0, 1 function. You could have taken a function which takes values in the interval 0 to b. Could be an arbitrary function which kind of just gives you confidence instead, and then here you will just get b over 2 instead of half. It doesn't, yeah, it's nothing special about 0, 1. I just like to think of the algorithm output as 0, 1 as yes or no. Okay. And the reason sort of KL divergence becomes interesting, as I said, is chain rules. So when you're trying to look at n samples, you want to look at the how much you can distinguish between the product distribution p to the n and q to the n, which is just the product distribution of n samples. P to the n and q to the n can be very hard to analyze even if p and q were very simple. But KL divergence is very easy to analyze because of chain rules. So a lot of the time, the way things are applied is that when you take many samples, you think in terms of KL divergence, and at the end, you just sort of relate it to L1 distances when you are actually talking of how well can you distinguish between two sample classes. And the name for this is Pinsker's inequality, which can prove here, but it just says that the KL divergence is greater than equal to some constant times the square of the L1 distance. What about the upper bound? Before I prove the lower one. Can I expect an upper? Sorry?
Infinite?
Yeah, so KL divergence can be infinite, so I can't quite expect an upper bound. So I can only expect a one-sided bound. I mean, the L1 distance between P and Q, by the way, I should have said earlier, is always bounded between 0 and 1. And you can just check it from the expression. So P of x adds up to 1, Q of x adds up to 1, and this difference between absolute values is at most P of x plus Q of x. Okay, good. So, and the way this is done is in 2 steps, and let's see how much time I have. I might do 1 or 2 of them, or both. But the first step is to just kind of think of a distribution which has a support of size 2. So instead of some complicated distribution, we'll just think of something which is 0 or 1. And these distributions are just as follows. Kind of all that matters for the L1 distance is whether P of x is bigger than Q of x or the other way around. So we'll just define these 2 subsets. So we'll define A as the set of all points where P of x is bigger than Q of x, or is at least as large. A complement will be the opposite, and we'll just define these distributions P sub A and Q sub A, which are just 1 or 0. All they care about is whether you landed inside A or not. So you could also think of it as a random variable, which is z, and z is equal to 1 if x is inside A, and 0 if x is not in A. Okay. And so P sub A and Q sub A are 2 distributions for the random variable z. You can just write them as a distribution or as a random variable directly. Okay. And now I can, because if I tell you X, you already know Z. I can think of P as a distribution for X and Z together. So I can think of it as P as a distribution for X and Z together. So I can just think of the KL divergence between P and Q as the KL divergence between these two distributions on this bigger support size, or on these two random variables, because Z is just something unique which you just tag on to X. It's not something which you need any additional freedom in the distribution for. So for every value of X, there is a unique Z. And now we just apply chain rules. So this is and the first term is exactly what we want. And the second one is non-negative. So yeah, I mean, it's just a chain rule. And notice that, so something to check is that the statistical distance, or the L1 distance between P and Q, is exactly the same as the L1 distance between PA and QA. And okay, yeah, that's something I'll ask you to check. Once we do this, the question just boils down to proving an inequality for a distribution supported on 2 points. I'll leave it here. I'll do this next time. But you can think of these distributions as with probability P, they are sort of 1 or 0, or with probability Q, it's 1 or 0. The L1 distance is just 2 times P minus Q. And you have some inequality which is between numbers P and Q. We can actually just prove it by sort of taking some derivatives, thinking of it as a function of one of these variables, and just proving some monotonicity. I'll do it next time to complete the proof, but yeah, you can also try it on your own if you like. I'll stop here. Any questions?
Can I ask a question about the graph entropy?
Yeah, absolutely.
Sure. I was wondering, so graph entropy is the minimum of the mutual information, right? And what is it like minimizing over? Is it, because it seems like
so it's minimizing over the choice of X and Y, of the choice of random variables X and Y, which are constrained by what the graph looks like. So, I mean, X is not really, we are not really free to choose much about X. X is arbitrary. X is uniform over the graph, or over the vertices. Y is the random variable which it's minimizing over. Y could have any distribution. It could be correlated with X in any way you want, as long as it satisfies the fact that Y always gives me an independent set, and that independent set always contains X. There could be many independent sets containing X for a given value of X, right? So there are many ways of possibly choosing Y and its correlation with the random variable X. And it's minimizing for all these choices. Sorry.
But if I choose Y just to be X, then I get the minimum to be 0, right?
Sorry?
Wait, when you say Y has to contain X, do you mean like the intersection is non-trivial, or do you like it has to contain all of X?
If Y is equal to X, the mutual information is not 0, right? The mutual information is as large as it can be if Y is equal to X. They are maximally correlated. You want to have less correlation. Right? Mutual information of when Y is equal to X is very high. It's not low. The conditional entropy is low, but the mutual information has 2 terms. I mean, intuitively, If y is
Oh,
equal
right.
to x,
So
then it tells you a lot about x.
Yeah. Sorry. So it's an upper bound probably.
Yeah, it can't be independent of x. The information will be 0 if it's independent. Yeah, but
Yes,
because of all these
sorry.
conditions, you can't quite take it to be 0.
Okay, got it.
Other questions?
Wait, sorry. What do you mean by y contains x?
Y is a set, right?
Yes.
So a set contains a vertex. So x is going to be a uniformly random vertex. Y is going to be a set of vertices, which is an independent set. And these two variables are going to be correlated, that for any outcome in your probability space omega, you will get a vertex x of omega and a set y of omega. And we will define these two functions always in a way that the set y of omega contains the vertex x of omega. Right? So, I mean, don't think of them as kind of random things. Think of them as functions.
Okay.
Okay. So, let me try to write. So,
okay,
let's try to think of some sort of underlying probability space omega. And we are defining two functions. We are defining x from omega to the set of vertices, and we are defining y from omega to the set of all subsets of vertices. And we are asking that you define these two functions to minimize the mutual information between the random variables, but with the condition that for every outcome in the probability space, y of omega contains x, it's a single element. So y of omega contains the element x of omega. So you are free to choose these functions as you want, except that you have to satisfy this condition that y of omega always gives you an independent set, and it contains the function, the sort of x of omega. So these are now functions. You have sort of potentially some freedom in choosing them, and you can see by these examples that you can design them in different ways.
So then when you say x is a function from omega to the set of vertices, like, sorry, when, like, if x is uniformly distributed over B, like
Right.
this is, like, I think about this as omega puts like 1 over n on each of the vertices in omega.
Precisely. So omega is some space which, again, you are free to design it the way you want. And you are allowed to choose any sort of probability distribution mu on this omega. And it has the effect that when you look at the distribution of x of omega as a result of choosing omegas according to this probability distribution, x of omega is uniformly distributed.
Okay.
Okay. So that's, yeah, so there's another element, which is not just the choice of functions, but the choice of this mu on the probability space.
And is there a separate, like, can I choose a separate distribution for y?
So when you say separate distribution, the distribution is different, but I think what you mean is separate probability space.
Yes.
Well, so what does a separate probability space really mean? It means that you can choose an omega prime in some other space, which is completely independent of the choice of this omega. No, because of this kind of condition between x and y, which wouldn't be satisfied.
Okay, I see. This is what.
Otherwise, you could have. And I mean, even if you could have, we can always kind of combine these two spaces together and think of a big probability space, and I'll just call that omega. So in some sense, we can always think of them as being defined on the same space. It's just that how they interact on that space.
I see. Okay.
Madhur, so is it right to think of there being a probability distribution on the pairs x comma y such that the marginal onto x is uniform?
Yeah, that's correct. But there's this extra property that
that y contains x.
Y contains x, and y is an independent set. Yeah. Yeah. So I mean, in fact, that's what we were sort of defining it before. But if you really want to define it more formally in terms of the random variables, then we define it as functions.
Nadir, going back to the very last slide we're on, what is this dp dq arrow dp xz? Yeah, what is the relationship of divergence PQ versus P joint XC QZ?
Wait,
is that an equality?
The previous slide, right? This one?
That should be an equality, right? Because Z is just a function of X. On the very on slide 12.
Yeah, there's an equality. I just said it can be written as, so I just drew an arrow for that, but it's equal. Yeah.
And then that's because, yeah, z is just a function of x.
Yeah. Well,
And,
it's yeah. So here, I kind of just defined p of x comma z so that this is an equality. And p of x comma z is something I just created, right?
yeah.
And I could create it because z is a function of x, yes. But it's also, I should emphasize that p of x comma z was not given to me. I just cooked it up. Other
Hey,
questions?
Mother, could
Yeah.
you re-explain what you were saying about total variation distance being like the bust one sample classifier?
Yeah, I mean, so here I'm just thinking of this f as a classifying algorithm. It's given a sample, and it's trying to tell you whether the sample came from P or from Q. And I'll kind of develop this point even a little more next time. But let's say the function, it sort of says 1 if it thinks the sample came from P, and if it says 0 if it thinks the sample came from Q. Any algorithm which kind of is trying to do binary classification, I can think of its outputs as 0 or 1, right? Mm-hmm. And I claim that the expression on the left is measuring how well it can distinguish the two distributions. You can think about it. I will sort of also explain it in a slightly different, with a slightly different expression next lecture.
Okay, I see.
That makes sense? I mean, yeah, roughly at least the classification problem is okay.
Yeah. Okay, yeah. This is, okay. You're distinguishing between the expectations. Mm-hmm. Sure.
Yeah, we'll talk first half of the next lecture will be about something like this. So.
Okay, yeah, thanks. That makes sense.
Okay, other questions?
Can I ask about on page 6, what does it mean for what does the tree represent again?
Page 6. Oh, so that's what is called a Boolean formula, where you are thinking of the leaves, or at the very bottom, you have some variables and you're trying to compute some function of these variables. And the way you are computing is using some sort of a circuit. So you have, you take a bunch of variables. I mean, this is a very special formula where you first compute the OR of some things, then you compute the AND, then you compute the OR. And even more so that like sort of you don't have any like two wires going out of the same gate, like two wires going up. There's only one wire going up from any node in the tree. So that's another way of saying it's a tree. It doesn't have cycles. In general, circuits can have cycles. As undirected graphs, they can have cycles. They're directed acyclic graphs. But this is really a tree, which is called a formula.
But what is this relation with the theorem on the left here?
So I claim that if you can, so yeah, this is something I kind of left a little vague. So this is just to give context, but if you can cover the complete graph with R bipartite graphs, then there is a formula of size k times R, or sorry, n times R for computing the function that I wrote down using circuits of the type that I just sketched. Okay. We don't really need this. I mean, you can just think of the problem of covering the complete graph with bipartite graphs as an independent mathematical problem. I'm just saying that the motivation came from circuit lower bounds or formula size lower bounds. And in particular, the paper of Newman and Victorson considers a more general formula lower bounds using the same kind of techniques of graph entropy.
Okay, so you're saying there's like two techniques to get the same bound? Is that?
I mean, no, I'm saying that the technique we used for proving how many bipartite graphs we need to cover the complete graph can also be used to prove formula lower bounds. And this is a more general question. What we proved actually ends up being a special case of formula lower bounds.
Okay, got it.
And then this paper kind of studies more general called for lower bounds for what are called De Morgan formulas.
Okay, thanks.
Any other questions?